Hello, my dear students. Welcome back to IK Sir Chemistry classes. Here we are in lecture number 7 on the chapter Symmetry and Group Theory. In this video, we will discuss symmetry group. First of all, let us see what is symmetry group. The complete set of symmetry operations that can be carried out on a molecule is called symmetry group of the molecule. Let us see it again. The complete set of symmetry operations that can be carried out on a molecule is called the symmetry group of the molecule. And the number of symmetry operations that can be carried out on a molecule is called the order of its symmetry group. If four symmetry operations can be carried out on a molecule, the order of its symmetry group will be 4. The symmetry group is also called point group due to following two reasons. All the symmetry elements of the molecule intersect one another at a common point. It means all the symmetry elements present in a molecule intersect one another at a common point, and the position of this common point does not change during any symmetry operation. And this is why the symmetry group of a molecule is also called its point group. Let us illustrate it taking example of H2O molecule. It contains C2Z axis of symmetry. It is twofold axis of symmetry and two vertical planes of symmetry, sigma xz and sigma yz. All these three elements of symmetry of H2O molecule intersect one another at oxygen atom. Notation for symmetry group or point group. The notation or symbol of a point group is given on the basis of symmetry operations that can be carried out on the molecule. The notation or symbol of a point group of a molecule is given on the basis of symmetry operations that can be carried out on the molecule. The symmetry operations that can be carried on the molecule depend on the symmetry elements present in the molecule. It means how many symmetry operations and which type of symmetry operations can be carried out on the molecule depend on the symmetry elements present in the molecule. Thus, the symmetry group of a molecule depends on the symmetry elements present in the molecule. Let us illustrate it again. The complete set of symmetry operations that can be carried out on a molecule is called its symmetry group or point group. And the symmetry operations which can be carried out on the molecule depend on symmetry elements. In other words, we can say that the point group or symmetry group of a molecule depends on the symmetry elements present in the molecule. There are two systems for the notation of point group, and these are Schoenflies system. It is concerned with the molecular symmetry, and the another one is Hermann-Mogin system. It is concerned with the symmetry of crystals. But in this chapter, we are concerned with the symmetry of molecules, that is molecular symmetry, and hence Schoenflies system will be adopted in the present video and in coming videos. Illustrative example: H2O molecule contains four symmetry elements: identity, two-fold axis of symmetry, and 2 sigma v, sigma xz and sigma yz. These are collectively represented by the symbol C2V. Thus, the point group of H2O molecule is C2V. There are four symmetry elements which are present in H2O molecule. These are identity, C2Z and 2 sigma V. And these are collectively represented as C2V, which is the Schoenflies notation for the point group of H2O molecule. To make complete list of symmetry operations, we have already seen that the complete set of symmetry operations that can be carried out on a molecule is called its symmetry group or point group. Now the question arises how the complete list of symmetry operations that can be carried out on a molecule can be made. And for this purpose, some points, some important facts should be remembered, and these are given below. During making a complete list of symmetry operations that can be carried out on a molecule, the following facts should be kept in mind. And the first one is it should include the complete set of symmetry operations should include all the symmetry operations that can be carried out on the molecule, leaving behind none. It means all the symmetry operations that can be carried out on the molecule should be included in the list, and no symmetry operation should be left behind. And the other important fact is that the symmetry operations should be distinct. For example, the symmetry operations C32 and C3 inverse about C3 axis of symmetry give rise to the same orientation, and hence they are not distinct operations, and only one of them should be listed and the other should be discarded. Let us illustrate it with diagram. It is BCl3 molecule. This is Z axis, which is C3 axis of symmetry. C32 operation means rotation of BCl3 molecule about C3 axis of symmetry by 360 degree by 3 into 2, that is 240 degree. If this molecule is rotated about z-axis by 240 degree, this Cl double dash atom will come to this position as in the orientation number 2. This is Cl double dash, and similarly other chlorine atoms also change their position. And C3 inverse operation means rotation of this BCl3 molecule about C3 axis of symmetry by 120 degree in anti-clockwise direction. And if this BCl3 molecule is rotated about z-axis by 120 degree in anti-clockwise direction, this Cl double dash atom will come to this position as in orientation number 3. This is Cl double dash, and similarly the positions of other chlorine atoms also change. Now let us see orientations 2 and 3 are identical, and therefore these two symmetry operations are not distinct. They give rise to the same orientation, and hence during making the complete list of symmetry operations, only one of these two symmetry operations should be listed and the other should be discarded. The symmetry operations should be non-redundant. It means the symmetry operations should not be more than sufficient. Redundant means more than sufficient, and the symmetry operations should be non-redundant. It means the symmetry operations should not be more than sufficient. For example, the symmetry operations C3, C32, C33 and C34 can be carried out about C3 axis of symmetry. Out of these four symmetry operations, C3 and C34 give rise to the same orientation, and hence C34 symmetry operation is just a repetition of C3 operation, and hence it is redundant, more than sufficient, and it should be discarded. It means only three symmetry operations C3, C32 and C33 can be carried out about C3 axis of symmetry. Let us illustrate it with the help of diagram. It is BCl3 molecule. C3 operation means rotation of this BCl3 molecule about z-axis by 120 degree. As a result, this Cl double dash atom will come to this position as in orientation number 2. And C3 4 operation means rotation of BCl3 molecule about z-axis by 360 degree by 3 into 4, that is 480 degree. If this BCl3 molecule is rotated about z-axis by 480 degree, this is 360 degree, and again by 120 degree, overall 480 degree. The orientation number 3 obtained is given here. This Cl double dash atom will come to this position, and now let us look at orientations 2 and 3 which are identical. It means the net result of C34 operation is the same as that of C3 operation. Thus, C34 operation is just a repetition of C3 operation and it should be discarded. Only three symmetry operations can be carried out about C3 axis of symmetry. If two or more rotation operations about an axis produce the same result, if two or more rotation operations about an axis produce the same result, the rotation operation with minimum value of n is retained and the others are discarded. Let us illustrate it taking example. The symmetry operations C6, 2 and C3 means rotation by 120 degree. Both these symmetry operations involve the rotation of molecule about an axis by 120 degree. Hence C3 is retained. Here n is lower and here n is 6, which is higher. The C3 is retained while C6-2 is discarded. C6-2 operation means rotation of molecule about an axis by 360 degree by 6 into 2, that is 120 degree, and C3 operation means rotation of a molecule about an axis by 360 degree by 3, that is 120 degree. These two rotation operations involve the rotation of molecule by 120 degree. They give the same result, and according to this statement, C3 should be retained because its n value is lower while C6-2 is discarded. Now let us see C1 point group. The molecules which don't have any other symmetry operation than identity belong to C1 point group. It means the molecules having only identity element of symmetry belong to C1 point group. Symmetry elements present in such molecule is E, and symmetry operations that can be carried out on the molecule is also identity, and the order of point group is 2 because the number of symmetry operations is 1, and therefore order of point group C1 point group is 1. The order of C1 point group is 1, and let us see an example. 1 bromo 1 chloroethane. This molecule contains only identity element of symmetry and no other element of symmetry, and hence it belongs to C1 point group whose order is 1. C2 point group. The symmetry operations are identity and C2. The symmetry operations, these are symmetry elements which are present in a molecule which belong to C2 point group, identity and C2, and symmetry operations that can be carried out on such molecule are C2 and C22, which is equivalent to identity, and the order of such point group, C2 point group, is 2. There are two symmetry operations, and let us see an example. H2O2 having open book structure. This molecule contains identity and this C2 axis of symmetry. If this molecule is rotated about this axis by 180 degree, a similar orientation will be obtained. C3 point group. The symmetry elements present in such point group are identity and C3, and the symmetry operations are C3, C32 and C33, that is E, and the order of C3 point group is 3. 1, 2 and 3 symmetry operations can be carried out, and let us see it's an example. Triphenyl phosphine, which has propeller structure, and this is C3 axis of symmetry. No other element of symmetry is present in triphenyl phosphine molecule, and hence its point group is C3. Ci point group. The molecules having only identity and center of symmetry belong to Ci point group, and the symmetry operations that can be carried out on such molecule are I and I square, that is E, and the order of point group is again 2. Let us see an example. It is a staggered 1,2-dibromo 1,2-dichloroethane, which contains a center of symmetry at the midpoint of carbon-carbon bond. This is Cl atom. If we move this chlorine atom to the center of symmetry and then to the opposite side by the same distance, and a similar atom will be obtained. Staggered 1,2-dibromoethane 1,2-dichloro. Staggered 1,2-dibromo 1,2-dichloroethane has center of symmetry and identity, it belongs to Ci point group. And now, what about Cs point group? The molecules having only identity and plane of symmetry belong to Cs point group, and the symmetry operations that can be carried out on such molecule are sigma and sigma square, which is equivalent to E, and the order of point group is 2. Let us see an example. NH2Cl chloramine. The plane bisecting the H and H angle. The plane bisecting the H and H angle and containing NCl bond is the plane of symmetry in chloramine molecule. This is NH2Cl. Now the plane which bisects H and H angle and contains NCl bond is plane of symmetry because it divides the molecule into two equal halves which are just mirror images of each other. This plane which bisects this angle and contains NCl bond is plane of symmetry, and no other element of symmetry is present in NH2Cl molecule, and hence its point group is Cs. Now the time for self-assessment. Find out the point group of following molecules: HOCl, quinoline, isoquinoline. Systematic approach to find out the point group of a molecule or ion. The point group of a molecule or ion can be determined in systematic manner. The point group of a molecule or ion can be found out, can be determined in a systematic way with the help of following flow sheet diagram involving some questions and their answers. Let us see it. First of all, the molecule whose point group is to be determined, we put a question: is the molecule is linear? If the molecule is linear, that is S, then we see is center of symmetry is present in the molecule. If center of symmetry is present in the molecule S, its point group will be D infinity H. And if center of symmetry is not present in a linear molecule, its point group will be C infinity V. It means linear molecules can have only two type of point group: D infinity H if it contains center of symmetry, and C infinity V if it does not contain center of symmetry. If the molecule is not linear, then we will see are two or more Cn present in the molecule. Are two or more Cn present in the molecule where n is greater than 2. If two or more Cn having n greater than 2 are present in the molecule, then we will see each center of symmetry is present in the molecule. If center of symmetry is not present in the molecule, its point group will be TD. And if center of symmetry is present in the molecule, then we will see each C5 axis of symmetry is present in the molecule. If S, its point group will be IH, icosahedron. And if C5 is not present in the molecule, its point group will be OH. Now, if the molecule does not contain two or more Cn where n is greater than 2, then we will see R and C2 dash perpendicular to Cn are present in the molecule. If S then we will see is horizontal plane of symmetry is present in the molecule. If S, the point group of molecule will be D and H, and if horizontal plane of symmetry is not present in the molecule, then we will see R and sigma D are present in the molecule. If and sigma D are present in the molecule, its point group will be D and D. And if N sigma D are not present in the molecule, its point group will be simply Dn. Now, if N C2 dash perpendicular to Cn are not present in the molecule, then we will see is Cn present in the molecule? N-fold axisymmetry. If Cn is present in the molecule, we will see is sigma H is present in the molecule. If sigma H is present in the molecule, its point group will be C and H. And if horizontal plane of symmetry is not present in the molecule which contains Cn, then we will see is n number of sigma v are present in the molecule or not. If n number of sigma v are present in the molecule, its point group will be C and V. And if n sigma v are not present in the molecule, then we will see is S2n is present in the molecule, where it is 2n, here it is n. Is S2n is present in the molecule? If S2n is present in the molecule, its point group will be S2n, and if S2n is not present in the molecule, its point group will be Cn. If Cn is not present in the molecule, then we will see each plane of symmetry is present in the molecule. If S, its point group will be Cs. And if plane of symmetry is not present in the molecule, its point group will be, then we will see each point of symmetry is present in the molecule. If plane of symmetry is not present in the molecule, we will see point of symmetry or center of symmetry is present in the molecule or not. If I is present in the molecule, its point group will be Ci. And if I is not present in the molecule, its point group will be C1. Thus, we see that the minimum symmetry of a molecule is C1, which has no any other element of symmetry than identity. Now the time for another self-assessment. Find out the point group of following molecules or ions: SF4, ICl4 minus, BrF4 plus, ethylene, para-dichlorobenzene, quinol, and ClF3, PdCl4 2 minus, CoCl4 2 minus, CONH3 5 times, Cl 2 plus, meta-dichlorobenzene, and hypochlorite ion. Thank you for watching the video with patience and concentration. Please like and subscribe my channel. And if you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.